So this, I guess this is it, because we're already in, yeah, it's past start time, I think. Yeah. So I'm guessing that everybody else is in the lab.
A lot of QRS does not really look like QRS. We're just talking about the fact that we do have some peaks.
Well, the QRS wave is going to be highly distorted by the various signal processing that you do.
Like,
so you're seeing something that looks more like this, right?
No, it goes down first. It goes in the trench first, comes up and...
Okay, so the polarity is completely arbitrary,
yeah,
because it depends on your electrode positions, right? Oh. So the polarity is completely arbitrary. You can get either polarity. And so you can't predict which of these you're going to see. And secondly, the high-pass filter is effectively a differentiator. So let's look at the Bode plot of, first of all, an integrator. A Bode plot of an integrator looks like this. This is log F, and this is log A, and this is an integrator. A low-pass filter looks like this, right? Therefore, for frequencies that are in the range of cutoff of the low-pass filter, the low-pass filter looks like an integrator. Same is true of a high-pass filter. Differentiator looks like this. High-pass filter looks like this. If the frequencies of interest are in the region of cutoff of a differentiator, of a high-pass filter, it looks like a differentiator. These signals are happening once a second, more or less, right? You're getting these signals once per second, which means that this has a frequency component around 1 hertz. If you're now setting the frequency, the frequency characteristic of the cutoff here to 5 hertz, then 1 hertz is going to be in the cutoff, and it's going to differentiate the waveform. So every high-pass filter is a differentiator at some frequency. Every low-pass is an integrator at some frequency.
So how do we get the exact QRS? Do we re-differentiate it?
How do you reconstruct the original waveform? Well, you have to undo the filtering. And to undo the filtering, you're also undoing the noise suppression. And so you can't do that very easily unless you have a very low noise signal. All you can get in this case is the interval between waveforms, which is preserved by all this ugly transforms that you're doing. So you probably are gonna need to, yeah, you can't get too much about the waveform from this. You can get the rate. At high gain, if the diff amp is set to high gain, and now you're talking, yeah, I think what do you set gain to? 5,000? Something like that?
But we have 2 stages. We have another one that's doing 160.
Is it AC coupled between them?
Yes.
Okay, that gets rid of the offset. Crystal, what'd your gain set to? Was it 2,000, something like that? So, yeah. It was very clear. Yeah. Well, so he's got like twice the upper body mass or something, right? Yeah, I guess I could believe that. So you'd think, now let's see how this scales. So the heart scales like, the volume of your heart must scale something like the mass of your body, because you're pumping blood throughout your body. But how does the dipole moment scale with the mass of the heart? It probably doesn't scale up with the mass because it's proportional to some size, right, which goes as the cube root of the mass. So you might be right. It might be a smaller person has a stronger signal.
But then permittivity of the skin, of the mass and the muscle might not be linear.
That's also true. And you ask, so what is the impedance of skin, and how does that depend upon any manner of different physiological characteristics? One thing is true is that testosterone tends to make thicker skin. And so you might guess that males on average have somewhat thicker skin than females do, and maybe higher impedance. I'm not sure that's true. I'm sort of making up a story here, but if you have this gain set to very high, so this is like times 4,000 or some very high value, any electrode drift, any input drift is going to saturate the amplifier, which is, I think, what you were seeing. And these electrodes are guaranteed to be within 100 microvolts of each other. But now you're asking for a gain that is going to saturate the amplifier at 100 microvolts. All right, so it just can't record it. So the solution is, if you want to try this, is to put coupling capacitors before the electrodes, and then a series of resistors after the electrodes, where these are as matched as possible, but not ridiculously. And you don't lose too much common mode rejection this way. So you might make these all 1 meg, 1% resistors, and this maybe be 1 microfarad capacitors. And that'll completely get rid of the electrode polarization because it's AC coupled away. It's still there, you just won't see it.
This is coupled to the ground, right? As 0.
This is coupled to 0, right? This is coupled to the whatever the neutral is for the input amplifier.
1 meg and 1 microfarad.
Yeah, that gives a time constant of about a second. Half second. So that's sort of a second order effect that I hadn't expected to see, but it makes sense at high gain.
Okay, in this case, would it help if the first amp had less gain and the other one had more gain? So you are effectively...
If you have low gain in this stage, followed by a capacitor coupling to the next stage, then you have gotten rid of all of the DC offset. And that is a conservative thing to do. Put a factor of 100 here and a factor of 100 here. Or, yeah, factor of 100 max. And you will have zero gain going into here. You'll have 0 offset going into the second amplifier, rather than trying to put all of the gain out here. What do you gain by putting all the gain out here? Well, you maybe gain a little bit better signal to noise ratio, but after you've amplified the input by a factor of 100, the dominant noise is not going to be amplifier noise anyway. So the noise added by the second amplifier should not matter very much. Anything else on lab? So, was anybody down in the lab before lecture? I was wondering how many people are down there from the class. Because, so I can start a new topic, or we can go down and work in lab. Any votes? Lab.
Yeah.
You okay with that?
Okay.
Oh, got it. You're not okay with it. You don't care, right? Yeah, that's fine. Crystal? Okay, so there's stuff you need to do in lab. Okay, so I'll write a nasty email saying, you know, being in the lab. Well, maybe I'll just go down to the lab and see who's there, and chew on them. Okay, let's go to the lab rather than starting a new topic.